one technique that is particularly useful when integrating complex functions is the method of changing the variable. Now, this might become clearer when we do some examples, but let me show you the proof first. If I show this here, I'm using capital F to represent that this is a function that has been integrated. And I'm going to say that this relates to the integral of lowercase f that has been integrated with respect to x. Now, if this is too complex for me to integrate straight out, I might want to try this method where I represent the variable x by some other function that is dependent upon some other variable. So I've changed the variable in question to t. I might find that this actually works slightly better. So what does this mean? Well, it means that y, that was equal to f of x, is now actually equal to f of phi of t instead. And what I'm going to say is that now that this function is a function of t, it's actually a totally different function now. So we'll call it g of t. If I wanted to differentiate g, then I could do that, but I'd need to understand how dy was changing with respect to t, dy by dt. And so I could do that by looking at dy by dx multiplied by dx by dt. And you can see that this one here, dy by dx, would be equal to the first order derivative of x. But what that would therefore be, it would be the first order derivative of this integrated function, and the derivation and integration would undo each other. And it basically would be just equal to the original function as a function of x. So, with that in mind, we can rewrite this function g prime of t would therefore be equal to f of x multiplied by dx by dt. So in this case, f of x, the original function, was f of phi of t multiplied by the first order derivative of phi of t. Now that means that g itself would be equal to the integral of f of phi of t multiplied by the derivative of phi of t. This is integration by changing variables. And this will become much clearer, I think, with an example. So a nice example, it could be, say we had kx plus b dx all to the power of n. We want to identify what this integral is equal to. Too complicated? Not if we replace the variable. So everything inside the brackets, let's consider that equal to t, kx plus b. Now that means that we could write it out in terms of x. X is, well, t subtract b, so it'd be t minus b and then divided by k. Now we could work out what dx by dt is of this expression, and of course this is just t minus b divided by k. So from our rules before, t minus b would be 1 over k. Now if remembering by what we have to do here is we have to take the original function and we have to multiply it by the first derivative with respect to t of that function. So if we were to then therefore do this, we would be basically taking the first of all the function itself, which was so the integral of t to the n multiplied by that first derivative, which would be 1 over k dt. Now, of course, the 1 over k can step outside because it is just a multiplying factor that does not itself depend upon t. So, therefore, we can have 1 over k, and then the integral of t to the n dx. Now, of course, we know how to handle situations like this. They're quite simple. So, it would be 1 over k t to the n plus 1 divided by n plus 1, a general solution to t to the n when integrated with respect to t, sorry, should be t there, with respect to t. So therefore, when we integrate this expression, which is kx plus b to the power of n by dx, we find that the solution is 1 over k t, which was kx plus b to the n plus 1 divided by n plus 1. Now this is generally true, and we can just replace k, b and n with any numbers that we so choose, and then using the method of switching the variable, we're able to therefore calculate what the integral will be of that function.